Good morning. It's August 30th, and this is your daily brief in science. Here's everything you need to know. A recent study reveals a potential link between weekend sleep recovery and reduced heart disease risk. Over nearly 14 years, researchers tracked more than 90,000 participants, confirming heart disease diagnoses through hospital records and cause-of-death registries. Participants were grouped by their weekend sleep duration, allowing for an assessment of how compensatory sleep impacts heart health. Those who reported the most weekend sleep were found to be 19% less likely to develop heart disease compared to those with the least. Experts suggest that adults should aim for 7 to 9 hours of sleep each night to avoid accumulating sleep debt, which can negatively affect overall health. Poor sleep is associated with various serious health issues, including high blood pressure, high cholesterol, and an increased risk of heart attacks. Additionally, sleep deprivation can weaken the immune system and impair cognitive function, underscoring the importance of adequate rest. However, while this study indicates an association between weekend catch-up sleep and better heart health, it does not establish a direct causal relationship. Experts warn that relying solely on weekend sleep may not fully counteract the negative effects of sleep deprivation accumulated during the week. The findings will be presented at the European Society of Cardiology Congress in London, highlighting the ongoing research into the relationship between sleep and heart health. To maximize the benefits of sleep, maintaining a consistent sleep schedule throughout the week is crucial. A breakthrough study published in the journal Science has unveiled a new energy source for the solar wind, linking magnetic switchbacks near the sun to the acceleration of the fastest solar winds. This research is based on data collected from both the Solar Orbiter and NASA's Parker Solar Probe, which indicate that fluctuations in the sun's magnetic field, particularly Alfvén waves, are crucial for heating and accelerating the solar wind. Recent measurements have revealed that the fastest solar wind heats up after it leaves the solar corona, a phenomenon that previously lacked a clear explanation. The Parker Solar Probe has detected that these magnetic switchbacks, which are fluctuations in magnetic field lines, may significantly contribute to the solar wind's acceleration and heating. Analysis shows that around 10% of the total energy near the sun is stored in the magnetic field, which diminishes to about 1% as the distance increases. This suggests that magnetic energy plays a vital role in plasma acceleration, enhancing our understanding of why the solar wind is hotter and faster than previously anticipated. Both the Parker Solar Probe and Solar Orbiter have measured the same plasma stream at varying distances from the sun, allowing for a detailed comparative analysis of energy transfer. The fast solar wind, which can exceed speeds of 500 kilometers per second, exits the corona at lower speeds, indicating there is an unknown mechanism responsible for its acceleration as it moves away from the sun. Jaime Rivera from Harvard and Smithsonian pointed out that while Alfvén waves were previously hypothesized as an energy source for the solar wind, this study provides definitive proof for that theory. Understanding the dynamics of the solar wind could have significant implications for the habitability of exoplanets, as highlighted by study co-leader Jaime Rivera. Daniel Mueller, ESA project scientist, stated that the combined data from these missions illustrates the interaction of various solar phenomena in shaping the sun's magnetic environment. The research team is now expanding their analysis to examine how the sun's magnetic field energy influences slower solar wind streams. A recent study has revealed a fascinating form of speciation that occurs not through geographic barriers, but through temporal separation. This research, published in the journal Proceedings of the Royal Society B, focuses on two closely related moth species found in the southeastern United States. The study investigates the nocturnal rosy maple moth and the diurnal pink-striped oakworm moth, which have evolved distinct activity patterns. Approximately 3.8 million years ago, these species diverged from a common ancestor, with the rosy maple moth being the only nocturnal species in its genus. Researchers discovered that differences in clock genes, particularly the disco gene, play a crucial role in regulating the moth's circadian rhythms. They identified 23 mutations in the disco gene that distinguish the two species, providing a clear example of evolution in action. The findings indicate that rosy maple moths allocate more energy to their sense of smell. while pink-striped oakworm moths have developed more genes related to vision. However, no significant differences were found in the genes responsible for color vision, suggesting that variations may exist at the sensitivity level. This research highlights the need for broader genetic studies across species, particularly as climate change continues to impact biodiversity. The brightly colored rosy maple moth is of particular interest to evolutionary biologists, offering unique insights into the processes of species formation. Lead author Yash Sondhi emphasized the importance of understanding the molecular mechanisms behind speciation and the necessity of characterizing a wider range of genes. A new research breakthrough may change the landscape of autism diagnosis and treatment. A multi-university team, co-led by University of Virginia professor Gustavo K. Roda, has developed a system that detects genetic markers of autism in brain images, with an accuracy ranging from 89 to 95%. This study underscores the strong genetic basis of autism and advocates for a genetics-first approach, which could significantly transform how the condition is understood and treated. The method employed, known as transport-based morphometry, or TBM, allows for earlier diagnosis and personalized treatment by focusing on genetic markers rather than waiting for behavioral cues. The findings from this research may help pinpoint specific brain regions and mechanisms that can be targeted for therapy, potentially leading to more effective treatments for autism. Published in the journal Science Advances on June 12, 2024, this research marks a significant shift towards a genetics-first perspective in autism studies. The TBM technique distinguishes between normal brain structure variations and those linked to autism-related genetic variations known as copy number variations, or CNVs. The research team utilized data from the Simon's Variation in Individuals project, ensuring accurate comparisons by carefully matching control subjects for age, sex, handedness, and non-verbal IQ. Unlike traditional machine learning methods, TBM is grounded in mass transport principles, offering a more biologically relevant analysis of medical images. This innovative approach addresses the limitations of conventional methods that often overlook the biophysical connections inherent in the data. The research was funded by several prominent organizations, including the National Science Foundation and the National Institutes of Health, with significant contributions from collaborators at the University of California, San Francisco, and Johns Hopkins University. A new study published in the journal Nature reveals the significant role of dopamine in the decision-making processes of male fruit flies, particularly in mating scenarios. The research illustrates how dopamine prompts these flies to prioritize mating over potential threats, indicating that this neurotransmitter is vital for their courtship behaviors. As male fruit flies engage in courtship, rising dopamine levels impede their sensory pathways, causing them to become less aware of dangers around them. Lead researcher Dr. Carolina Rezaval highlighted that while courting, male fruit flies often overlook physical threats, including simulated predators introduced during the study. Interestingly, when specific neurons associated with dopamine are silenced, these flies continue their courtship even in the presence of threats. This suggests that these neurons play a crucial role in determining whether survival instincts or mating instincts take precedence. The implications of this behavior extend to humans, as noted by Dr. Lisa Scheunemann, who pointed out that people may similarly ignore dangers when pursuing a goal. Additionally, the study found that dopamine release is associated with rewarding experiences, which reinforces memory formation related to those experiences. The research involved genetically modified fruit flies to investigate how dopamine mediates the relationship between different types of memory. This collaborative study across multiple institutions received funding from various scientific organizations, contributing to a broader understanding of decision-making mechanisms that may also exist in mammals, including humans. First author Cheng Huang, inspired by his childhood curiosity about memory, played a significant role in uncovering how different brain regions influence memory formation. The study aims to shed light on how innate responses to stimuli affect the formation and retention of new memories over time. This has been your Daily Brief in Science. To read more about these stories, follow the links in the episode bio. You can also subscribe to these updates via email at www.brief.news. For more daily podcasts about the topics you love, visit brief.news/podcasts. We'll be back Monday with everything you need to know.